Hey, it's Mr. Kabbalah. In these recap videos, I'm going to try to take the lesson or lessons and condense it down into the most important parts. So please let me know if you have any questions, and enjoy.
So I think the most important thing in lesson number 1 of unit number 8 is the ratio of sides of similar right triangles. So first of all, these are right triangles. I measured them out. I actually measured 8 centimeters, 6 centimeters, 10 centimeters, 12, 9, and 15. We can test to see if these are right triangles by doing the Pythagorean theorem. 6 squared plus 8 squared is 10 squared. 9 squared plus 12 squared is 15 squared. So those are right triangles. Now, what I'm talking about from the lesson is something like this, where we can compare side lengths between the two triangles, and we notice that the ratios are all the same. What I'm talking about is if we take corresponding sides, like this 9 and this 6, so 9 over 6, and do some division, so 9 divided by 6, I get 1.5. If I take corresponding sides 12 over 8, I also get 1.5. Corresponding, these happen to be the hypotenuses, 15 over 10, 1.5. So between the two triangles, there's a constant ratio, 1.5. But also interesting is within each triangle that these have equal ratios. Now, we'd also have to point out that this angle here and this angle here are the same. Also, this angle right up here and this angle right up here are the same, and I've already marked the 90-degree angle. So that's something we have to keep in mind, that these are similar triangles. They would have the same angle measurements, but their side lengths might be different. So taking a look here, we're going to, again, take a look at corresponding sides. If I do 6 over 8 and do that division, I get 0.75. If I do the corresponding sides within triangle B, 9 divided by 12, I also get 0.75. 6 divided by 10 is 0.6, and so is 9 divided by 15. 8 divided by 10 is 0.8. 12 divided by 15 is also 0.8. 8 divided by 6 is 1.3 repeating. 12 divided by 9 is 1.3 repeating. So notice when you compare corresponding sides within each triangle, the ratios are the same. What I'm going to do now is construct two similar triangles. I'm going to speed it up so you don't have to watch the whole thing. I'm simply going to ensure that the angles are the same. You'll see that the side lengths are different, and then we're going to investigate what happens from there. So here we go. I'm just going to arbitrarily pick side lengths and go from there. So I paused here just to indicate that what I was trying to do is I'm keeping this angle right here the same as this angle right here. Okay, so what I've done so far is I've made two right triangles. So let me mark the 90-degree angles right there and there. Now keep in mind that I'm a human, so I might have a little error here, but let's do a little measuring to see how long these side lengths are. So this one's roughly, let's say, 15.1. This side is about 10.5. Now we could use the Pythagorean theorem. Let's just check that real quick. We could take those two sides, 10.5 squared plus 15.1 squared, and then take the square root of that. So our hypotenuse should be about 18.4. Let's just see if we're close. Hey, not bad. Okay, let's do this one. Now I'm going to measure the hypotenuse first. I'm going to say about 13.2. Let's take this leg, about 10.8. Okay, let's do the Pythagorean theorem, but we're going to find the side of the missing leg here. So 13.2 squared, this time I'm going to subtract 10.8 squared, take the square root of that answer. So that should be about 7.5 or 7.6, so let's see how we did. Not bad. I got about 7, well, yeah, 7.5. Imagine that. Kind of worked out. So we have these two similar right triangles, and what makes them similar again is that their angles are all the same. You can kind of see right there. Those two angles are the same. Those two angles are the same. And obviously the two 90-degree angles are the same. All right, but what isn't the same are the side lengths. So we're going to first compare the ratio between the two triangles. So let's call this one C. Let's call this one D. So I'm going to take corresponding sides from D and divide them by C. So let's start with the hypotenuses. I'm going to take 13.2, divide by 18.4. Now, again, keep in mind, I am human, so there might be some error. So these might not be exact, but they'll be close, or they should be. Let's hope. Okay, so about 0.72. I rounded. All right, so now let's take this bottom leg, 10.8, and we're going to divide by the bottom leg here, corresponding side, 15.1. Now, because we're going between the two triangles, hopefully this will be right around 0.72. So 10.8 divided by 15.1. Hey, 0.72. And then finally the last two, 7.5 compared to 10.5. And again, if we account for some error, but it should be close, about 7.72. 0.71, but pretty darn close. So between the two triangles, there's a constant ratio, okay, called the scale factor. But now let's take a look at the ratio of side lengths within each triangle and compare those ratios between the two triangles. So what I'm talking about is, let's first take triangle C here, and let's do this bottom leg 15.1, and we're going to divide it by the hypotenuse 18.4. So 15.1 divided by, that's clear, 15.1 divided by 18.4, and I'm going to round about 0.82. But now let's take the corresponding sides in triangle D. So again, we did bottom leg to hypotenuse. So let's take bottom leg 10.8 to hypotenuse 13.2. Now, even though the side lengths are different, okay, if we did everything right, this should be about 0.82. 10.8 divided by 13.2. Pretty darn close, 0.818, which is 0.82 if you round it. Okay, now let's do another ratio. Why don't we take the leg going this way, so 10.5, compared to the hypotenuse, 18.4. So 10.5 divided by 18.4, and we get about 0.57. If we take the corresponding sides in triangle D, which again is going to be 7.5 and 13.2, hopefully we'll get something close to 0.57. 0.568, which rounds to 0.57. And then we could do a bunch of them, but let's just do one more. Why don't we take, let's say, 10.5 and 15.1. So the two legs, 10.5, 15.1. We get about 0.695, which is about 0.70. right? So again, we're going to take corresponding sides 7.5 and 10.8. And if we did everything right, that should be about 0.70 divided by 10.8, which it's close, 0.69 tee. But it's pretty darn close. Again, there's some human error in there, but you can see that what I'm trying to get at is that between the two, so going from one to the other, there's a constant ratio called the scale factor. But then within each one, if they're similar, the ratio of corresponding sides are the same between each triangle. And that's going to become important as we move into trigonometry. Now, just to drive the point home, what I did is I created a big similar triangle. So again, I kept this angle down here the same. I have the 90-degree angle right down here. So I know it doesn't look it, but they are similar. You can match up the angles like that. So let's call this triangle E. And I'm just going to do one set here. I'm going to measure, if you remember, when I did 10.5 divided by 15.1, 10.5 divided by 15.1, I got 0.70. So I'm going to measure corresponding. So for this side, I get about 19 centimeters. And again, keep in mind, there's human error. Okay, along this one, I get about 27.6. And so, if we take those, and just like we did 10.5 divided by 15.1, if I take 19 and divide by 27.6, hopefully we get something close to 0.70. And we do, 0.69. Okay, it's pretty darn close.